All right, so welcome everyone to this One World Mathematical Physics seminar. So this talk, as all our talks, is going to be recorded and you can then watch it on our YouTube channel. Okay, so today it's my pleasure to introduce Rupert Frank, who's going to talk about eigenvalue bounds for Schrödinger operators with complex potentials. So please go ahead.
Okay. Well, thank you very much for the invitation. It's a pleasure to be here and to see so many familiar faces. I want to talk about, as you said, about Schrödinger operators with complex potentials. Let me just see okay, good. There's probably, again, the problem with the black thing.
Yes, but for now it's not obstructing anything important. Oh, now it is.
Yep. Okay. Well.
Yeah, no, it's all right.
Okay. All right, good. So anyway, right, as you said, I'm going to talk about these eigenvalue bounds for Schrödinger operators with complex potentials. And this has been a rather active field in the past 20 or 15 years. And in particular, last month, there was the solution of one of these bigger problems in the area by Bergley and Cunin. And I thought this is a good opportunity to review this subject, summarize what is known, and also emphasize some problems that are still open. Okay, so the setting will always be, for me, Schrödinger operators on RD. D can be any dimension. And what I will assume about the potential, besides that it can have complex values, is just that I know that it lies in LQ for some Q. Now, I will always want to have this Q less than infinity, which means that in some sense, the potential is small at infinity. Okay. On the other hand, I also want to have Q sufficiently large just so that I can make sense of this operator. For instance, there's a version in this world which is called, in this non-self-adjoint world, which is called M sectorial operators. Don't worry too much about this. But the point I want to stress is that all the information about the potential I want to encode in this LQ norm of the potential. And under these assumptions, it's quite easy to see that the spectrum of this resulting operator outside of the positive real line consists only of eigenvalues of finite algebraic multiplicities, and they do not have any accumulation points in this complex plane without the positive axis. So if they can accumulate, they can only accumulate on the positive half axis. Okay, I'm stressing this because there has been in the past 20 years, as I said, quite a lot of analysis of non-self-adjoint operator. And so people have tried to understand, of course, I mean, the spectral analysis will never be as complete as in the self-adjoint case. But people have studied situations where you have a lot of non-self-adjointness. And what I want to emphasize here, that we have rather little non-self-adjointness in the sense that this potential is really a local thing. It lives sort of, and at infinity it's very small. And that's reflected in the fact that somehow we still have this, just like in the self-adjoint case, this thick spectrum from 0 to infinity. And outside of that, we just have eigenvalues. Okay, and our interest will be, what can we say about these eigenvalues? And more precisely, I always want to think about what we do know in the real case. And of course, somehow what pops in mind there are libertarian inequalities. And I want to ask myself, to which extent these results carry over to the non-self-adjoint situation. And as we will see, the situation in the complex case is quite surprising and actually quite crazy, much more crazy than one might think at first sight. And so I want to structure this discussion into 3 parts. Let me, first of all, I want to ask myself about bounds for individual eigenvalues. So I'm asking myself, remember, I always want to take the LQ norm of the potential as my fixed quantity. And given this LQ norm of the potential, I want to ask myself, how large can the eigenvalues be? Or put differently, in which region of the complex plane can these eigenvalues lie? Secondly, I want to talk about sums of powers of eigenvalues. So not only information of a single one, but also about the possible accumulation of these eigenvalues. And the third item will then be, we try to say something about the number of eigenvalues, but this is only in its infancy. And as I mentioned already, there was great work recently by Berkeley and Cunin, but many questions in this area still remain unresolved. So let me start with this first item that I mentioned, namely when we talk about single eigenvalues. And let me look for comparison at the case of real potentials. Okay, so if real potentials going to 0 at infinity, then the eigenvalues can only accumulate at 0, so they lie somewhere in the negative real line. And I ask myself, well, how far can they lie away from 0? Right, so that's the interval where they can lie. And then I have the following bound. I have the eigenvalues are within a certain distance that's given purely by the LQ norm of the potential. Okay, now you can think this just follows from scaling, right? Because the eigenvalues scale like 1 over length squared. Now you take this to a power, do the integral such that it works. That's almost right. I mean, you need, of course, to have some a priori information, but essentially you have an interval whose size is controlled by the Q norm. That is reminiscent of a question that Keller asked in 1961, where he asked sort of an isoperimetric problem. How small can the lowest eigenvalue of a Schrödinger operator be, a self-adjoint Schrödinger operator, right, be given the LQ norm of the potential? And so he did some formal heuristic analysis, and independently of that, Lieb and Thiering in 1976 asked the same question and answered it, and observed that you have such bounds. Okay, provided the parameters satisfy these restrictions. These are very natural restrictions. In dimension 1, you want to have a power of the potential which is greater or equal than 1. And in higher dimensions, well, this power gamma that appears here can be arbitrary. And the first question that I want to ask is, how much of this situation that Keller and Lieb-Thiering proved there, how much of this does survive for complex potentials? And so this story starts with work of Brian Davis and co-authors in 2001, and they proved in one dimension that each eigenvalue, now of this complex Schrödinger operator, right? So the eigenvalues can lie anywhere in the plane. Each eigenvalue lies in a disk of a radius that's controlled by the L1 norm of the potential. Okay, which is very nice, and this looks exactly like this bound of Keller and Lieb-Thiering that we have up there. In fact, not only does it look like it, the optimal constant in this bound of Keller and Lieb-Thiering is 1/2. So you have exactly the same bound in the complex case as you have in the real case. And so then when you're an optimist, you would think, well, perhaps the same is true in general, right? Perhaps in any dimension with the complex potentials, you have exactly the same inequalities. Perhaps there's some sort of maximum principle or something going on in the background, and you can just carry over the real inequality to the complex case. And that hope is wrong, okay? And so there's a very simple example that we gave in 2011, where we look at the operator, same one-dimensional operator as in the previous work, but now on the half line with a Dirichlet condition. And what we showed there is, in this case, you need to increase this constant by a factor 2. Okay, and so instead of 1/2, it's 1. And you cannot improve the 1. And so it's not, I mean, I don't want to insist here on the value of this, I mean, that you have to multiply by 2, but I think it's a good indication of what really is going on. Okay, so first of all, it shows you that it's very unlikely that you have an argument that just as a black box takes the real inequality and makes it work in the complex case. All right, so that's the first indication that you, I mean, here we just see that we have to change the constant, but really later on we will see that we actually also have to change the range of exponents. Second thing is, when you look a little bit more closely at where the eigenvalues can lie, here's a picture up there from this paper. So I said the eigenvalues lie in this disk, which has twice the radius. Right, that would be the whole disk here. Now, actually, the eigenvalues lie in a smaller region, namely this region bounded by the dark black curve. And that's where the eigenvalues are, multiplied correspondingly with the L1 norm of the potential. And what you see when you look at this picture is that here the eigenvalues with negative real part, they are almost as good and as nice as in the self-adjoint case. The trouble starts with eigenvalues way over here, close to the tip of this curve. Right? These are the eigenvalues that are close to the positive real axis. And these will be the troublemakers throughout the talk. These are problems that do not occur in the positive case. So we're talking about eigenvalues that are very close to the positive real axis. And these eigenvalues will destroy a lot of the things that we know from the real case. And as I said, we see the indication already when you look at this very simple example. So let me tell you here on this slide what is known about this Scalar libertarian question. Okay, so remember, we want to find a disk which contains whose radius scales like the appropriate power of the LQ norm of the potential, which contains all the eigenvalues. And in 2009, Laptev and Safronov conjectured that such a bound holds at least when gamma is small or not too large. They arrived at a number gamma less than d over 2. Exactly how they arrived at this number, I'm not so sure. I think they were thinking somewhat in terms of Wigner von Neumann potentials. These are potentials in the self-adjoint case that have embedded eigenvalues. Anyway, their conjecture was that at least for this restricted range of gamma, you do have a bound just like in the self-adjoint case. All right, and in 2011, I was able to prove that at least in a restricted range. Okay, so instead of the d over 2 that they had conjectured, I could prove it up to 1/2. All right, there's a little small print. They originally only conjectured it for non-real eigenvalues, whereas actually it turns out that the inequality is true even for real eigenvalues, but that's a minor detail at the moment. And so the question was then, what happens if you go beyond 1/2? I mean, was there a problem with my proof? Did I not get the whole range? Or is there really something going on beyond 1/2? And so this was the result that I mentioned, which was, whose preprint appeared about a month ago. Bergli and Cunin showed that actually the inequality does not hold when gamma is greater than 1/2. Okay, so they showed that such an inequality does not hold with a finite constant whenever gamma is greater than 1/2. And this finally settles this Laptev-Safronov conjecture, So it holds in a certain range and fails in another range. And just to give you a clue of how strong this conjecture is, or rather its failure is, once you have proved this theorem here, that there is no such bound, what you get is that there's a potential, okay, which is not too bad local, which is bounded and decays sufficiently fast such that the eigenvalues, this thing here occurred, such that the eigenvalues occur at every, I don't know how to remove this, sorry. Okay. Oh, it's always when something in the chat appears, then, okay. Okay, good. So the statement was that once you have this theorem proved, meaning once you have shown that no such inequality can hold, then you get immediately that there's a potential which is bounded and decays sufficiently fast such that every positive real number is an accumulation point of the spectrum. Okay, so the eigenvalues were the cloud which sits around the complete positive half-axis. Every point is an accumulation point. And you can get this with a potential which is locally nice and decays sufficiently fast at infinity. And moreover, somehow this, this number, the precise exponent, the L d plus 1 over 2, that's the exact exponent, the decay exponent that makes this possible. So that is really quite, I mean, shows you how bad the spectrum can behave and how different from the real case. Now, the question that you might ask yourself is, of course, now what happens at gamma equal to 1/2? Why is there a threshold? Why do we have in the self-adjoint case, we have no restriction on gamma, and why in the complex case, we have suddenly this restriction where it holds on one side and does not hold on the other side. And so I cannot completely explain this, but let me give you a little bit an idea of how the proof works. So this is now sort of from this paper where I proved the inequalities, and the recent counterexample tells you sort of that this proof idea has some optimal features. Now, what was the proof idea back then? Well, if you look at eigenvalues, it's natural to look at the Biermann-Schwinger operator. And once you look at the Biermann-Schwinger operators, then resolvents are very natural. Okay, now, as I told you also, what you're interested in are points very close to the positive real axis. So you're sort of in the setting of what's known as a limiting absorption principle. You want to look at the resolvent and you hope that the norm of the resolvent does not go crazy as you approach the positive real axis. And such bounds were actually proved by Koenig, Ruiz, and Zog. And for a certain range of p's, about which we will talk, you have a bound on the resolvent considered as an operator from LP to LP prime. P prime is the Hölder dual of LP, with a certain bound on in terms of the spectral parameter. But the important thing is that this bound is completely uniform in the angle, right? So in the argument as you approach the positive axis. Therefore, these inequalities are called uniform bound. And these are rather deep theorems, and they are essentially equivalent to something called the Stein-Thomas inequality in harmonic analysis. Let me not explain you exactly why they are equivalent. You can just imagine, I mean, when you have the resolvent approach the spectrum, then you get sort of a delta function, right, from the resolvent. And the Stein-Thomas inequality is sort of the inequality for that delta function. Very roughly speaking. So what's the setting of the Stein-Thomas inequality? So there you're given a function on the sphere, L2 function on the sphere, and you Fourier transform this. More precisely, you look at this function, I mean, think of it as a measure that sits in RD, which is just concentrated on the sphere. And that measure you Fourier transform. And now you ask yourself, this Fourier transform, which is now defined in all of RD, what decay property does this have? And the theorem is that there's a certain exponent such that this Fourier transform taken to that power and integrated is finite. All right. And what you see is that this power here is the Hölder dual of that power. And that's, again, by some simple duality argument, gives you exactly the power gamma equal to 1/2. Anyway, I understand that this doesn't explain much, but let's talk a little bit more about this inequality. Namely, what I want to tell you is about a thing that's very well known in harmonic analysis, namely the so-called NAP example. Right, so we were talking about this inequality where you have an L2 function on the sphere, and I want you to pick a particular L2 function on the sphere, namely one which is supported on a tiny little cap around the North Pole, say. Okay, so let's call this the size of this cap, the radius, let's call that epsilon. And then, of course, somehow, since the sphere is curved, in the z direction, you have a size epsilon squared. Okay, and so now as I told you, you want to compute this Fourier transform over here. And then just by scaling of the Fourier transform, the Fourier transform will look very much like a needle, right? Like a cylinder, a long cylinder, where now d-1 directions scale like 1 over epsilon, and the remaining direction scales like 1 over epsilon squared. Okay, there's one long direction and d-1 short directions. And these guys show, when you do the computation, just plug this thing in, show you that you cannot improve that power. Okay, so this means that you cannot improve that power, which means that you cannot improve that power. That's roughly the situation. Let me get a little bit more concrete. There was a interesting paper by Ionescu and Jerison, where they constructed a Schrödinger operator with a real potential that has an embedded eigenvalue. And moreover, the potential is essentially supported in such a region. Okay, and this is a different phenomenon from those Wigner von Neumann examples of embedded eigenvalues, because you have this non-radial structure. And so to put now this Berkeley-Cunin example into context, they essentially showed that one can push this eigenvalue off the positive real axis. And to summarize that discussion, again, so I understand that what I told you now was perhaps more for specialists in harmonic analysis. Perhaps the takeaway message is that not radial potentials are the enemies, but these very elongated potentials, which are sort of essentially supported in cylinders. Right? Those are the guys that Berkeley and Cunin use to violate this inequality. And yeah. And if you have that in mind, then there are a couple of results. I want to go quickly through them. Those appeared in the years when people were trying to prove this conjecture. And they suggest now things how you can go beyond this threshold gamma equal to 1/2. Namely, one thing is, and this is where this power d/2 comes in, you do have the inequality for radial potentials. Okay, so the original Laptev-Safronov conjecture is true when you have radial potentials. Or more generally, you can have arbitrary potentials, but when you compute the norm, you need to first take the supremum over the angles. And then this was a result by Berkeley in 2017. She already showed that this assumption d over 2 is optimal. She constructed radial potentials actually, which violate such a bound beyond d over 2. Okay, so the takeaway message is for radial potentials, d over 2 is the threshold. For general potentials, gamma equal to 1/2 is the threshold. And then, well, going back to general potentials, what can we say? Can we say anything if gamma is greater than 1/2? And the answer is yes. And let me show you again this picture that we had there. So there we had this curve, and the curve somehow bent down and touched the real axis at a finite point. Now, what one can show is that the eigenvalues lie in a similar region, except that this thing here, this tip, stretches out to infinity, and it decays in a certain power-like fashion. Okay, so there's a thick ball sitting there, and then there's a tiny little cusp stretching out to infinity. That's the meaning of this bound. This is a bound which holds beyond 1/2. And you see there's a choice is made here. I mean, I write, instead of e to the gamma, right? I write e to the 1/2, and then I take another quantity to the power gamma minus 1/2. What is the other quantity? That's smaller than absolute e. I mean, that's a thing that deteriorates as you approach the positive axis. And roughly speaking, what this new paper of Berkeley and Kühner also shows is that this power that appears here is optimal. This is, roughly speaking, think of this as the power of this cusp that stretches out to infinity. Okay.
Excuse me,
Yes.
this funny curve, does it have a simple description? Is there a formula that describes it?
I mean, it's just, I mean, it comes from this formula, right? I mean, you write this in terms of the real part and the imaginary part of E. And that gives you sort of a curve, right? I mean, it is explicit, sort of.
Thank you, yeah.
But I don't think it has a particular name or anything. But the point I wanted to stress is that so it has a power-like decay, and this power-like decay, which is encoded in these exponents, that is optimal. Does that answer your question?
Yes.
Right, I mean, there's a power which let me call it 1 over x to the 5, and the eigenvalues are within, below this curve, 1 over x to the 5. Something like that. Mm-hmm. Okay, and you can saturate this power 5. All right, anyway, so this is the situation that we have for single eigenvalues. And I want to go over to the second part of the talk and ask, what can we say about several eigenvalues? Okay, and once again, we can go and look at what's known in the real case, and there are the inequalities of Lieb and Thiering from 1976, plus an endpoint case of Weidel 20 years later, which say that not only can the individual eigenvalues be bounded by an integral of the potential, but actually their sum. Right? Let me go back. I mean, that's a very remarkable theorem, right? The Keller's question was, can you bound a single eigenvalue by this power? And what Lieb-Thiering showed is not only, yes, you can, but also you can bound the sum of all these quantities. So this bounds somehow, well, I mean, how big the eigenvalues altogether can be. And this holds under the very same assumptions under which you have a bound on a single eigenvalue. Once again, the question is how much of this survives for complex potentials. And so we wrote a little paper in 2006 together with R. Laptev, Elliot Lieb, and Robert Schrödinger, where we showed essentially that if you stay away from a cone around the positive real axis, then everything is just as nice as in the real case. Okay, so take a cone around the axis, and outside you have the good bounds. Put differently, what we really should care about are these eigenvalues inside cones around the positive real axis. This is similar to what I told you before. The eigenvalues close to the real axis, those are the real troublemakers. And the bound we proved back then has a very explicit behavior on the size of this cone, right? As the cone becomes smaller, as the bound deteriorates, and we estimate how much it can deteriorate. And what you can do, if you want, is you can integrate this bound with respect to this kappa, and then you get a different bound, which is weaker, but is perhaps a little bit nicer, and which will also be relevant for what follows. Okay, so what you get is now, right? So you just integrate this bound with respect to kappa, and then you get expressions of the following type. So first of all, you have the eigenvalues to the power gamma. This is just like over here, like what libertarian had. And then you have a factor. This is a factor which is bounded by 1. It's a factor which is equal to 1 in the left half plane. So for eigenvalues with negative real part, I don't do anything. I just have the ordinary libertarian sum. But then as I approach the positive real axis, this factor tends to 0. So I'm sort of making the influence of the bad eigenvalues smaller. And then, as I said, integrating this bound here, you arrive at such a bound where you have the eigenvalues, then times this factor to a certain power bounded by the potential. All right. So here is what is known about such inequalities. Don't look at this thing too carefully. Let me just explain you the structure. We have eigenvalues to a certain power. Right? That's what we would like. Then we have this additional factor whose strength is controlled by beta, which deteriorates as you get to the positive axis and does nothing for the eigenvalues in the left half plane. So far everything is just like in the bound we just looked at, but now I allow for a different thing, namely I allow for the sum to be taken to a power. All right, and then I'm asking myself, for which exponents, alpha, beta, and gamma, can I bound such a quantity by an alcunum of the potential? And the theorem that you see down there
Sorry
says,
to interrupt.
Yes.
Just to point out a question in the chat by Michael Hutt. The question is, can you throw away the positive real part of V in the complex case? So what can you do with the real part of the potential?
No, at least we don't. I mean, I share sort of the impression or the feeling that this should be less relevant. But since we do not have a variational characterization of the eigenvalues, I do not know how to say something like this a priori. That said, I mean, there were some attempts also by Laptev and Safronov to look at the different parts of the potential differently. I don't think there is a definite answer to this question yet. And so for simplicity, I mean, I think this inequality is already complicated enough as it's written. I just put here the absolute value for V. But in general, I agree. I mean, it would be nice to understand better which parts of the potential contribute to which extent. All right. So what I wanted to say is that there's a theorem here which says that for certain values of these parameters, such an inequality holds. I don't want to go through all these things now. I'll point out on the next slide some particular items. But before doing that, let me stress one particular, well, understandable case of the inequality. Namely, once again, let's go to one dimension. Let's take the potential in L1, just like in this inequality of Davis and collaborators. And then what you have is the eigenvalues, the distance of the eigenvalues to the positive real axis, summed, and then taken to the power 1/2. This is smaller than the integral of the potential, right? So this should be compared with the Libertarian inequality, actually Weidl's endpoint case of the Libertarian inequality. And there you have the 1/2 power inside, right? In these theorems here, we need to put the 1/2 power outside, which makes it a weaker inequality. And we'll talk about that later. So here are a couple of remarks about these very complicated bounds that we looked at on the previous slide. The first question is, imagine we already had these examples, right? Eigenvalues can accumulate at the positive real axis. So the natural question is, how fast do these eigenvalues accumulate? And so again, here's our power gamma equal to 1/2 appearing. If gamma is less than 1/2, then you can prove the inequality with a beta equal to 1. So we want to have beta as small as possible. This means that if the eigenvalues accumulate, then they are summable, meaning they accumulate fast. Okay, this is the best result there is at the moment. This is somehow related to analytic functions. You know, there's the so-called Blaschke condition that you ask about the accumulation of zeros of analytic functions, and then summability is sort of essentially the best you can hope for. Another point that I want to emphasize is this power here, the gamma divided by alpha. This is something that is not present in the Libertarian inequality, right? In the Libertarian inequality, you bound a sum by an integral. In fact, that's very important for the applications that the Libertarian inequality has in the stability of matter and in density functional theory. It's sort of a local inequality, right? So if you have a potential which consists essentially of two disjoint parts, then the right side of the Libertarian inequality is just the sum, and sort of the eigenvalues, well, they also, I mean, they are not exactly the disjoint union of the two eigenvalues, but up to some small tunneling they are. And so the Libertarian inequality quantifies in a non-asymptotic regime such a locality, how the eigenvalues depend on the potential. That's a very important feature of the Libertarian inequality, and it explains one of its uses. And so if you're critical about this inequality, then you might ask, well, we tried to prove Libertarian inequalities, but we didn't manage because we were not able to reproduce this locality that's so important for Libertarian. Now the point and the question that is behind is, I mean, is this a deficiency of the proofs? Have we just not found the correct proof or the correct form of the inequality? Or actually, is it true that this locality feature that's behind the Libertarian inequality, that this is just not there in the complex case? That's a valid question. And I don't have a complete answer. I think this is one of the most exciting questions in this area. But I do think we tend to believe that actually you do lose this locality feature. So in particular, there's a result by Cunin who showed, remember there's this inequality here, where I told you in the complex case, you have to put the 1/2 power outside, right? That's the comparison to the self-adjoint case, and thereby you lose locality. You have a square root over sum. And Cunin showed that you need to do that. You cannot have the inequality with, a better inequality where you have more of the power, more of the 1/2 inside and less outside, if that makes sense. So that really tells you in some sense that at least for this very particular case in one dimension with L1 potentials, you lose this locality features. There's a similar result by Berkeley and Stampach, where they were able to disprove another bound which would have shown a locality feature. So what I like about these results is that at least in some cases, this theorem, as ugly as it looks, actually is optimal. It's best possible. It would be nice if we could clarify when exactly it is best possible. And let me make another remark here about the techniques of the proofs. I will be very short, but essentially there are two techniques how you approach these questions about Schrödinger operators with complex potentials. The first one, for the lack of a better word, I call an operator theoretic approach. This goes back to Cato and was significantly strengthened by Hansmann 10 years ago. This is where there you look at general, essentially compact operators, and you compare singular values of these operators. There's an unperturbed operator and a perturbed operator, and then you apply those to the Schrödinger framework. You have to deal with the fact that Schrödinger operators are unbounded and so on, so you need resolvents. But the essence of the material is an inequality about singular values of compact operators. And then there's a different approach which uses analyticity. I already alluded to this one before. So, just like for matrix, right, the eigenvalues are the zeros of a determinant. In that spirit, you cook up an analytic function whose eigenvalues whose zeros are exactly the eigenvalues you're looking for. And then you're left with doing two things, namely, number one, you have to prove theorems about analytic functions. And there's a particular nice work by Borchev, Kolinsky, Kupin, where they, you have an analytic function in the upper half plane, and you know what sort of bounds you have. Typically these bounds have singularities at some points of the boundaries, and you show how they are reflected in the distribution of zeros. And then the other thing is you have to bound the determinant now. And there, if this Stein-Thomas theorem, or these uniform resolvent bounds, gave you information about the single eigenvalue, then it's perhaps not so surprising to hear that Schatten ideal versions of such bounds give you information about several eigenvalues. Right? Boundedness of an operator gives you information about a single eigenvalue. Schatten ideal versions, so quantifying compactness, gives you information about several eigenvalues. And so that was the second approach, how some of these theorems on the previous slide here were obtained. I told you there were these two approaches. It seems to me that they are rather disjoint. each of the two approaches has its advantages and its disadvantages. But what no one has been able to do is to combine these two approaches and kind of combine their strengths. And this is, again, an open problem. And I think that would perhaps help to improve and well, beautify these results. Anyway, that brings me to the last part of this talk. We've talked about individual eigenvalues. We've talked about sums of eigenvalues. Now, the last point is we want to talk about the number of eigenvalues. We do the same thing as always. We look first at the real case. Okay, so we ask ourselves, with a real potential, when does such a Schrödinger operator have finitely many eigenvalues? When does it have infinitely many eigenvalues? And the answer is well known and is contained in the classical books. And it says that the threshold between finitely and infinitely many eigenvalues is a 1/x² decay at infinity. Okay. So if you decay faster than 1/x², then you only have finitely many eigenvalues. If you decay slower than 1/x², think Coulomb potential, then you have infinitely many eigenvalues. Again, the question that we would like to ask is how much survives of this situation for complex potentials? And there is a resounding nothing given as answer already in 1966 by Pavlov. And let me state the results of Pavlov in one dimension for simplicity, essentially proved that the threshold in the complex case is on the exponential scale. And more precisely, if your potential decays like e to the minus constant times square root of x, then you have only finitely many eigenvalues. And if you decay like e to the minus constant times x to the alpha, with an alpha smaller than a half, then you may have infinitely many eigenvalues. Okay, so this is much, much more subtle, or much more sense. The question about finitely versus infinitely many eigenvalues is much more sensitive to the decay. And already for a rather rapid decay, you could have, I mean, faster than any polynomial, right? You could have infinitely many eigenvalues. Now, this result of Pavlov was proved using complex analysis, and actually serious complex analysis. I mean, this it's quite deep. And I should also say that this is, so the first result, that you only have finitely many eigenvalues, that this was proved essentially by contradiction. Okay, so this result that he used, proved from complex analysis, this gives, I mean, it's by contradiction. It says if you would have infinitely many eigenvalues, then this and that would occur. So therefore, the question that is natural at this point is there a quantitative version of the first part of Pavlov's theorem? And what do I mean by this? Well, imagine you have an explicit bound, right? So you bound the potential. Let's just say two parameters, right? I mean, one parameter, the parameter B, that's related to the inverse length scale on which this potential lives, and D, which is the strength of the potential. Can one give, so if alpha, let me say it again, if alpha is 1/2 or greater or equal than 1/2, then according to Pavlov's theorem, we only have a finite number of eigenvalues. Can anybody give me a bound on this number of eigenvalues depending on the two parameters D and B? That's what I mean by a quantitative version. So imagine, I mean, you have a, I mean, of course, if you can scale really, this by scaling, there's really only one dimensionless quantity. You can ask, I mean, for instance, in the strong coupling limit, how fast does the number of eigenvalues grow in that limit? Now, the case where you have such a decay with alpha equal to 1 is relatively easy. Just if your potential decays exponentially, then you can continue the resolvent across the spectrum onto a second sheet, and then you can use inequalities from elementary complex analysis to get bounds. So the really interesting case is, can we do something like this when alpha is between 0.5 and 1? And I don't know the answer. There's a little toy problem that we studied recently where we do the thing in the discrete setting. Meaning, instead of looking at Schrödinger operators on the half line, we look at Jacobi matrices. Okay, meaning tridiagonal matrices. If you think the A's and the C's, you can, if you want, just take them equal to 1, or I think in the convention I'm using here, take them equal to 1/2. And then the B's play the role of the potential. Okay, that would be a discrete Schrödinger operator. And similarly as before, I mean, now the essential spectrum is -1, 1, and we're interested in the eigenvalues outside, more precisely in their number. And we want to assume that our potential satisfies such bounds like I wrote down on the previous slide, right? D is the coupling strength, and B is related to the inverse length scale on which this potential lives. And well, what we proved in this paper are bounds. Okay, so for instance, if you have in the critical case, right, where you have exponential to the minus constant times the square root of x decay. There we prove, for instance, fix the length scale, just look at the strong coupling limit, right, D. We prove that the number of eigenvalues cannot grow faster than exponential. Actually, exponential of square root of the coupling parameter. Okay. And similarly, there are bounds if you assume that the potential decays a little bit faster, but still not exponential. Okay, these bounds I know are not particularly nice. Let me comment a little bit on them, and then I will be done. So how do we prove these? Well, the answer is again by complex analysis. So we imagine we have a function, analytic function in the unit disk, and we want to get bounds on its number of zeros. And what we actually show is an optimal theorem. Okay, so this problem from complex analysis we completely solve. Let me. Yeah, okay. So the question is now, having an optimal theorem from complex analysis about analytic function in the unit disk, how can you translate this to Jacobi matrices? Because of course you want to apply this to a determinant, some perturbation determinant, modified perturbation determinant. The question that lurks in the background is it true that these analytic functions that you get as perturbation determinants, that they are significantly better behaved than analytic function in the disk? Or differently, can these functions be as bad as any analytic function in the unit disk? Okay, if it would be the second case, then I mean, since our theorem is optimal for analytic functions, it would also be optimal for Schrödinger operators. This is a question that we don't know. Right? So in particular, I told you, I mean, what we can do here is we can say that the number of eigenvalue does not grow faster than exponential of square root of the coupling constant. I don't know of anybody who has constructed a Schrödinger operator with so many eigenvalues. I mean, with the number of eigenvalues that grows so fast. There are a few examples, again, in these works by Berkeley, Stampach, and Cunin, where they show that you have, at least in one dimension, that you can have at least slightly more eigenvalues than in the real case. Of course, this is not a precise mathematical statement because you need a parameter in the game to talk that you have much more eigenvalue or much less eigenvalues. But I think it's fair to say that we're lacking examples where you really have as many eigenvalues as these bounds, all these bounds predict. And or conversely, it might be an interesting problem also to construct operators which, I mean, it's a question from inverse spectral theory. So given a certain analytic function in the unit disk, construct a Schrödinger operator who has that analytic function as its perturbation determinant. Okay, so I think these are all rather interesting questions. And let me end here with something that's perhaps a little bit of a dream. But if you remember going back, this exponent gamma equal to 1/2 and this NAP example, right, with this long needle. And there's a famous work of Pfefferman who disproved the so-called disk multiplier conjecture in harmonic analysis. And he did that by not only considering a single needle, but combining them. Okay, in a very complicated and ingenious way. And in this way, he constructed counterexample to this. And so one might wonder, I mean, since Berkeley and Cunin showed that these needles have something to do with eigenvalues of complex Schrödinger operators, can one use something like this Pfefferman construction to construct really lots and lots of eigenvalues of these non-self-adjoint operators? I don't know the answer, but I think that would be very nice if one could go into that direction and continue this correspondence between harmonic analysis and eigenvalue theory for Schrödinger operators with complex potentials. Anyway, that's all I wanted to say. Thank you very much for your attention.
Thank you very much. Thank you for this nice talk. Okay, the floor is open for questions. Are there any questions? Hello?
Maybe I can ask something.
Hi.
Hi.
Hi. So first of all, thanks a lot for this beautiful talk. And I kind of expected you to say something about resonances. In other words, in situation when you have potentials, you have real potentials, modulation, analytic or exponentially decaying, then you can deform them, and you can go to non-self-adjoint operators to study resonances. And in this particular case, maybe understanding neighborhood of zero could be simpler.
Yes, that's a very natural point. And indeed, this is one of the probably most natural situations where these Schrödinger operators with complex potentials arise. We have not particularly studied these cases, or somehow, or put differently, we have not looked at whether these general bounds improve in these situations. We have, in fact, let me say, like, there were, in these 10 years, there were many attempts of different people to try to disprove this conjecture. And some of these proofs were exactly based on these ideas that you have using dilation analyticity to make the eigenvalues discrete. And I think there are also works by Swirsky, and I think Nakamura had also results in that. So the question is something like this: to which extent can you apply techniques of dilation analyticity to embedded eigenvalues in the spectrum, like in the Wigner von Neumann potential?
Right.
Or to these examples of Ionesco-Jerison, which are a different class of embedded eigenvalues. And this is what people have tried intensely. I don't think they've succeeded, but I think this would be very interesting to understand better dilation analyticity techniques in the presence of embedded eigenvalues.
Okay, thank you. It's actually, I didn't know about this result of Pavlov, but the result of Pavlov also, you can think about this as a deformation technique, which is used also in multidimensional case. Assuming your potential decays exponentially, decays at infinity, then you can deform the there's a spectrum deformation technique using the flows in the momentum space in this case, because in momentum space you have an elasticity, and I think that also probably the Jan had a papers long time ago about going into the second Riemann sheet for maybe many body operators. I don't remember.
Yes. Yes, though I'm not sure whether you can really reach this square root, right? I mean, it's exponential of minus a square root, where you cannot extend it beyond the spectrum.
Right.
That's sort of a little bit mysterious, or I'm lacking an intuitive understanding of where this e to the minus square root of x comes from.
Mm-hmm. Okay.
Thanks.
Okay, thank you.
Thanks for the question. Any more questions, comments? Okay, that doesn't.
Sorry, can I ask? Did you consider the case of semi-exist and the dependence? This estimate dependence on the boundary condition, the boundary order, on the parameter of the boundary condition.
Can you say the first sentence again? Did we consider what?
I mean, one-dimensional case on the semi-exist, Schrödinger on the semi-exist.
Oh, okay.
And dependence on the boundary Robin parameter in boundary condition.
Yeah. Okay. So I mean, when you have these bounds, for instance, here.
Yes, you may have bounds for certain parameters and missing of these bounds for other parameters. I mean this.
Yeah. I mean, you can think of this as a delta potential sitting at the origin, and therefore the bounds that involve L1 norms, they generalize and give you bounds for the boundary conditions. At the same time, so in that sense, yes, we do have some bounds. On the other hand, I think one can also ask some quite deep questions about these boundary conditions. And it's, in fact, if one looks carefully at this Pavlov paper, what he does is he actually studies a real potential with a complex boundary condition. So it's really only the boundary condition which destroys everything. And for instance, I don't know about boundary conditions in higher dimensions, what one can say there, or again, what one can say in a one-dimensional situation about most boundary conditions. Yeah, I guess there are also interesting questions there, yeah.
Because it might happen that sometimes it may be a finite number and sometimes infinite. I mean, exactly, depending on boundary conditions.
Yes. And as far as I understand, for Pavlov, it's only, I mean, a single value of the boundary condition that gives you infinitely many eigenvalues. So I don't know whether one could have this for more boundary conditions as well, this phenomenon.
Thank you.
Thank you.
I still have a question, probably similar to Israel's question. I mean, there are quite a number of papers about resonances, counting resonances.
Yes.
This is not precisely the same the same setup, but it seems to be very closely related.
It is, yes, it is.
So how different are methods? I mean, there are quite a number of papers by Zworsky, by Sjostran. So how different are these two topics? And how different are the methods and the results?
So, I mean, one difference, I mean, a fundamental difference is that especially people around Zworsky and Sjostran, they usually assume infinite smoothness. So their results depend on, I mean, both their results and their proofs depend on quite a number of derivatives of the potential. So from that point of view, the techniques are quite different. We rather want to follow this idea of libertarian, of just using the LP norms. That's one thing. On the other hand, there are similarities to the extent that they also look very much at analytic functions and also use theorems about analytic functions to deduce these theorems. What should I say? I think, I mean, we would like, so we are certainly aware of these works, and we would like to use some of their techniques to answer, for instance, these questions about constructing many eigenvalues. But I think even if one looks at these papers by, you mentioned Zworsky, Stepanov is also somebody, also the question about resonances is a very unstable question. So to some extent, we run exactly into the same difficulties as they do, that they have upper bounds, but the optimality is perhaps only proved generically. And not, I mean, what I want to say is there can be occasionally situations where something goes bad to a rather large extent. And yeah. Well, and I mean, one thing that people like to do when studying resonances, they like to prove average results, where they try to get rid of these, what I just mentioned, I mean, about of these exceptional events. And that goes even to the extent that they perhaps look at random potentials, and they try to get bounds only averaged over this randomness. These are things that we have not yet tried, and where I'm also not sure to which extent they carry over, or yeah. I know that this is a complete answer, a satisfactory answer, but I think, yeah, it's interesting what they do.
Okay, are there any more questions, comments? Okay, I don't think it's the case anymore. So thank you once again for a very beautiful talk. So can